In section 1.3, we're going to talk about the states of matter. And what we mean by that are the state that it currently is in, such as being a solid, a liquid, or a gas. Now, it's pretty straightforward if you're just looking at it, and I just give you a container and say, hey, the stuff inside this container, is this a solid, a liquid, or a gas? But we're going to be talking about this stuff more on the molecular scale. So first, let's look at the physical properties, the properties something has just by nature of what it is without having to change it into something else. That's what physical properties are. But the physical properties of substances while they're in a solid, a liquid, or a gas state. And then after that, we'll talk a little bit about what's happening with the molecules to get them to act like they do in that particular state. Well, solids, as we know, are rigid. They don't flow like a liquid does. They don't move all over the place inside of their container like a gas does. And they have a shape like a chunk of ice or a rock. And that shape doesn't change. They stay in that particular shape and have whatever particular volume that they have when they start. Now, a liquid is not rigid. This flows, so it kind of takes on whatever shape the container has that happens to be holding that liquid at that particular moment. It does, however, have very specific volume. Even though it might flow around inside of a container, you're not going to end up with a larger quantity or a larger volume of it. It will be the same volume, perhaps just in a different location or in a different shape. Now, a gas, on the other hand, the main thing that differentiates the two, liquid versus gas, is the fact that there is no fixed volume. Gases can expand. You can actually squash them down, which you can't do for the other two forms of matter, other two states of matter, solid and liquid. So gases are what they refer to as compressible, a compressible state of matter. And so why is a solid a solid? Well, these things are arranged where the atoms or the molecules, molecules just being a collection of atoms bound together to form a specific substance, they're bound together here, though, in a certain way so that they cannot move relative to each other. Okay, so they can't move relative to each other. They can vibrate a little bit, they can kind of stretch or shake a little bit relative to their neighbor, but this particular atom, for instance, is always going to be right next to this one and that one and the other one. It's not going anywhere. They're attached, and although it may wiggle a little bit, it will be rigidly held in that particular location in space relative to the other pieces. And it does this because its attraction of one molecule to the next, or one atom to the next, is stronger than the energy that's causing it to move around. A liquid, though, the energy that the substance has increased so that the energy of attraction between one molecule and another molecule, or one atom and another atom in a substance, is now no longer strong enough. That attraction between them isn't strong enough to hold them rigidly into place. It is strong enough so that they have to stay touching each other, but they can kind of roll around the outside of each other and through the solution, being in contact with one atom or molecule after another, but they're always going to kind of stick to each other. The way I kind of picture this is if you have magnetic marbles, for instance, you can kind of slide them around each other and put them into different shapes and different arrangements, kind of representing the different shapes that a liquid forms depending on its container. You actually can't get them to come apart from each other. They still stick to each other, even though they take on different shapes. Okay, so what form does that make? Well, if it's in a glass, it's going to be the form of the glass. If it's spilled on the ground, well, it's going to be spilled on the ground. If you're in space, you have to think about, why is it that something takes the form of this cup when it's a liquid? Well, gravity is pulling it down. As it pulls it down, it's stopped by the physical shape of the container and just sits there. If you take it away from the physical shape of that container, it's still going to be pulled down by the force of gravity. It might spread out a little bit, but it's basically being pulled down into whatever it's in contact with. In space, however, you can see this little globule, and we'll watch a video here in a second that shows this. But this little globule is occurring because the liquid molecules, the little parts of the compound that make up the liquid, are attracted to each other and not being pulled down by gravity. So they're just pulling at each other and staying stuck to each other, and the way they can kind of maximize that attraction to each other is by the formation of a sphere. So let's watch that video. Now a gas is a little bit different. There's nothing that's strong enough here in a gas to hold them together so that the energy, that temperature energy which causes them to move, is much stronger than the attractive energy that's holding these particular atoms or molecules of this compound together. So that means they just fly off on their own, have no real interaction with each other, and they might bump into each other and ricochet off, but there's not going to be any sustained contact between one atom and another while it's in the state of matter that's a gas. So we can kind of classify matter also into a variety of different forms. So not only can we talk about whether something's a substance or, whether it's a solid, a liquid, or a gas, but then we can start looking at it in a variety of other ways as well, such as whether it's a element, which means that it is only one kind of atom. So since it's only one kind of atom, it can't be broken down into smaller pieces and still be an element, still be an atom that's intact. Now, a compound is just what you get when you take atoms and you attach them together in very specific ratios. So if I take a hydrogen atom and another hydrogen atom, and I put that together with an oxygen atom, that combination is the molecule water. And if all I have is a bunch of those exact combination of hydrogen, oxygen, hydrogen that make up water, then that's still a pure substance, but this is what we're going to refer to as a compound. So that compound being one set of properties, the entire contents of that glass, for instance, act like water, but yet if I went into this and applied the right amount of energy in the right way, I could split off a hydrogen, I could split off the oxygens, I could split off the elements, the atoms of a particular type that make up this particular compound from each other. So the test here for the first side of matter classification, that of a pure substance, is, can I separate it into simpler substances with their own properties? So for water, for instance, liquid at room temperature, if I separate it into simpler substances by breaking it down, I end up with things like, not helium, but I end up with things like hydrogen, which is a gas, and oxygen, which is a gas. So it's a new substance once it's split apart with its own set of properties. So instead of a pure substance, I can also have mixtures. Alright, so what's a mixture? Mixture is just multiple things in the same vicinity with each other. So if we go to the seashore, for instance, we can talk about water and sand and gases that are mixed with that water and sand, and there's salt and all sorts of other things in there, and those are all mixed in. And I can also talk about something like a glass of tea with some sugar in it. You know, the sugar's all mixed into the tannins and other things that cause the flavor and the color and the water that's in there as well. But what's the difference between these two mixtures? The difference between mixtures can be whether it is something that you can see the individual layers of and discern those individual portions, and that would be a heterogeneous mixture. Another quality of a heterogeneous mixture is that if I take a little bit from one part and then take a little bit from a different part, I'm going to get a different ratio of the different parts of that mixture. So in the close-up, if I say grab a sample right here, all I'm going to get is water. If I grab a little portion of the beach here, I'm going to get some sand and some water. That's the sand here on the bottom. And if I just grab a piece of this mixture right here, all I get is sand. So I get different things depending on where I am in that particular sample or mixture. Now with tea, if I grab a little bit here, or here, or here, or here, as long as I've stirred it well enough so that it dissolved well, I'm going to get the exact same ratio of sugar and tea and color and flavor anywhere in that particular cup. So when that's the case, where it's uniform throughout the entire sample, meaning it's the exact same ratio of things through the whole sample, then that's referred to as homogeneous. Now we can look at a couple of these examples and we can try and classify. Let's look at A first. Would that be a mixture or a pure substance, first of all? When we look at A, and we see that everything looks exactly the same. So whatever this is, it's pure. There's not more than one type of thing present here. And so it's not a mixture. Then we look at the things and say, all right, are they composed of different types of atoms? Well, we have some red, we have some black, more red. This is actually representing carbon dioxide. And one carbon with two oxygens. So since we have carbon atoms and oxygen atoms, this is not an element. An element would be just carbons or just oxygens present. And since we have both types of atoms, then this is a compound. This is a pure substance. There's only one type of thing. And this is a compound because it is not just one type of atom. It's multiple types of atoms, but bonded together. Okay, so let's look at B. Right. So when we look at this, we see that there's this molecule, which is actually an oil type molecule. An oily, organic-y type substance. And we have all these things that we can kind of recognize as water down below. So we have water and oil, and the way this diagram is showing it, that means that there's more than one thing present. So it's not a pure substance. If it's not a pure substance, our only other option is that it's a mixture. And since this is a mixture, we have to look at whether it's a homogeneous, meaning the same ratio all the way throughout, or a heterogeneous mixture, meaning I have different amounts of stuff of the different kinds, depending on where exactly it is in the mixture. Well, here I can see that all of this oily carbons and hydrogens portion are all at the top, while all of the water is at the bottom. So this is not a uniform mixture. Not uniform. So that means that this is heterogeneous. A heterogeneous mixture, specifically. Okay. So let's look at this one. Well, in this particular sample in C, we see that there's more than one type of molecule. So it's definitely, again, it's a mixture. Now, I also look at whether it seems to be kind of evenly distributed. And it's not always easy to tell with these diagrams, but it is kind of distributed out. I don't have one very distinct layer like I did with the oil and water up above. So we can kind of guess that what they're talking about is a homogeneous mixture. So this is much more uniform, so we're going to say that this is a homogeneous mixture. Excellent. Okay, so let's look at D. Well, it's all the same. Whatever it is, it's all the same, so we're going to say this is a pure substance. There's not more than one type of thing present. Now we're going to look and say, are these more than one atom, more than one sphere attached to each other? No. It's the exact same thing. It's just whatever the white spheres represent, all I have is white spheres. So in that case, it's only one kind of atom. This is the pure substance that we define as an element. So when we think about separating things, we can think about separating them by their physical or chemical properties. Now, physical properties are things that we can separate out just by things like their states of matter, for one thing. We'll talk more about this a little bit later. But we can have two liquids, for instance, and we can separate them out by turning one of them into a gas, and then it evaporates out and expands. And then as it cools down, it turns back into a liquid. And we can collect it down this little side arm in a condenser. Now, this is a mixture of two different liquids initially, but we can actually separate them out by the physical property of one boiling faster than the other. So we're taking advantage of that physical property. We can also separate solids from liquids just by pouring them through some sort of filter that doesn't allow the solid to go through, but does allow the liquid to go through. So while this might be a mixture, and a solid that's mixed in with a liquid is typically a heterogeneous mixture, but we pour this through, the solid sticks on top of the paper, and the liquid goes through. We've separated them, the parts of a mixture, just based on their physical states of matter characteristics.